Hello everyone, my name is Utkarsh Arora and I am presenting my internship project on microwave oven simulation using a PIC microcontroller. This project was completed as part of my internship at Emertxe Technologies and I am currently pursuing my studies at Bhilai Institute of Technology, Durg. The primary objectives of this internship were developing embedded software using embedded C for the PIC microcontroller to control microwave oven functions, working with both hardware and simulation by analyzing schematics and testing using PICSimLab, optimizing system performance by improving efficiency, response time, and resource management, testing and validating the firmware to ensure it meets design specification and works correctly with hardware integration. This presentation will cover the project requirements, key topics learned during the internship, the working of a microwave oven, cooking modes implemented, embedded system overview, microcontrollers versus microprocessors, development tools such as MPLab, XID, and PICSimLab, the PIC16F877A microcontroller, the block diagram of the microwave oven, peripherals like the matrix keypad, interrupts, timers, and the CLCD display. For the project, I have used MPLab XID and XC8 compiler for firmware development, PICSimLab for simulation and testing, PIC16F877A microcontroller as the main controller, 16x4 CLCD for displaying cooking time and modes, matrix keypad for user input, timer 2 for precise time tracking, LM35 temperature sensor for monitoring food temperature, fan, heater, and buzzer for system operations and feedback. During the internship, I gained knowledge of programming concepts such as arrays, pointers, strings, loops, and macros, embedded systems fundamentals, and microcontroller architecture. Development tools like MPLab, XIDE, XC8 compiler, and PICSimLab. Working with hardware components including switches, keypads, CLCD, timers, and interrupts. A microwave oven works by generating microwave radiation at 2.45 GHz using a magnetron. These microwaves excite water molecules in food, causing dielectric heating. The oven is controlled by a microcontroller which manages power levels, cooking time. It interacts with relays, sensors, and user inputs to ensure proper operation. I have implemented 4 cooking modes in this project. Micro mode. It uses a magnetron to generate microwaves for uniform heating and cooking by exciting water molecules in food. The maximum power used is 900 watts. Grill mode. It activates a heating element to provide direct heat, ideal for toasting, grilling, browning food surfaces. User can set time accordingly. Convection mode. It utilizes a fan and heating element to circulate hot air, enabling even baking and roasting, similar to an oven. It is used for preheating, which will take 180 seconds. Start mode instantly starts or increments cooking time by 30 seconds at the last selected power level for quick reheating. An embedded system is a dedicated computer system with a larger device. It includes hardware such as microcontrollers and sensors and software that is the firmware designed for efficiency and real-time operation. Types of embedded systems. real-time embedded systems for time-critical applications, standalone system that functions independently, network systems that communicate over networks, mobile embedded systems designed for low power consumption. Yeah. A microcontroller is an integrated system with CPU, RAM, ROM, and peripherals used for specific tasks like microwave control. A microprocessor, on the other hand, is mainly a CPU that requires external peripherals for operation commonly used in general purpose computing. The differences are microcontrollers have inbuilt memory and I/O, whereas microprocessors rely on external components. Microcontrollers are optimized for specific tasks, while microprocessors are designed for general computing. Microcontrollers consume less power, making them ideal for embedded systems, whereas microprocessors require high power. Microcontrollers use embedded firmware while microprocessors require an operating system. MPLAB XIDE is the software used for writing, compiling, and debugging code for PIC microcontrollers. PiximLab allows for simulation, reducing the need for physical hardware during the initial development. The development process usually involves writing and compiling code in MPLAB XIDE, loading the compiled hex file into PiximLab for virtual testing, then debugging and modifying the firmware before final implementation on actual hardware. The PIC16F877A microcontroller is a 40-pin chip with multiple I/O ports, timers, ADC inputs, and communication interfaces. It has 5 ports for digital and analog operations. It has timers which can be used for precise time tracking and event scheduling. It supports USART for communication with external devices, and it has interrupts which are used to respond to external events like key presses or timers. This is the block diagram for our microwave simulation. The PIC16F877A microcontroller is the central controller. The matrix keypad allows for a user input. The CLCD displays time and mode selection. The LM35 sensor monitors temperature. The fan, heater, and buzzer are controlled by microcontroller to manage cooking functions. And timer 2 is used for precise timing operations. A 4x4 matrix keypad is used for user input. It is connected to the microcontroller through row and column scanning. The microcontroller sets one row high at a time and checks which column is active. A debouncing delay is used to prevent false trigger. The key is mapped to a function such as number input start or mode selection. Interrupt service routine allows the microcontroller to handle time-sensitive tasks efficiently. How does it work? When an event like a key press or time expiration occurs, the CPU pauses the current task. It then executes the specific ISR function to handle the event. After processing, the CPU resumes the main program. ISRs are used for handling inputs, timing operations, and ensuring smooth system execution. Timers provide precise time delays and event scheduling. In this project, I have used timer 2. So how does it work? For example, with an 8 millihertz clock and a 1 is to 16 prescaler, timer 2 increments every 2 microseconds. After 125 counts, it triggers an interrupt every 2 milliseconds. By counting 500 interrupts, the system keeps accurate 1 second time tracking for cooking. A character LCD is a type of display module commonly used in embedded systems to show alphanumeric characters. These displays are popular due to their simplicity, ease of use, and low power consumption. The 16 cross 4 CLCD used in this project displays cooking time, mode selection, and system status. It communicates with the microcontroller using the standard HD44780 interface. So, how does it work? uh, Data is transmitted in 4-bit or 8-bit mode through GPIO pins. The LCD controller maps ASCII values to character patterns. The display updates dynamically to reflect real-time changes in settings. So this concludes my presentation on microwave oven simulation using a PIC microcontroller. Now I will show you the code and the demo. We will look at the code and simulation for the microwave oven simulator. The project is divided into header files for function prototypes and macros and corresponding C files that implement the logic. In main.h, we declare core function prototypes and macros. Uh, in clcd.h, we provide routines for the 16 into 4 LCD. In matrix keypad.h, we declare core function prototypes and macros to manage the 4 cross 3 keypad. In timers.h, we configure timer 2 for cooking durations. So main.c actually runs the main loop for the project. First, the LCD is initialized, then we initialize the matrix keypad, and then we configure timer 2. This line runs an infinite loop that checks for keypad inputs and updates the display. Then we have the code for mode selection, which helps to switch between micro, grill, convection, or start mode based on key presses. So the rest of the code is for controlling the fan, updating the display, and checking for open door conditions. Now that we have looked at the code, let's build the project. This will generate a hex file which we can load in PiximLab. Now let's load the hex file into PiximLab. So in PiximLab, our simulated microwave oven include these main components. Uh, Fan automatically turns on whenever a cooking mode starts simulating airflow. If cooking is paused or stopped, the fan turns off. Buzzer. It emits a beep when set cooking time is up or if door is opened mid-cycle. Heater is used during grill and convection modes for direct or circulating heat. LCD displays cooking modes, time and user prompts. Keypad allows for mode selection, time entry and cooking control. RB3 button simulates microwave door. Pressing it interrupts cooking and triggers the buzzer. Now let's look at the four modes. We can set the time using the keypad. To enter, we need to press hash symbol, or if we want to clear the time, we can press star symbol. By combining these hardware elements with four modes and keypad controls, this simulation closely replicates a real microwave oven's functionality. Thank you, Emergee Technologies, for providing this internship, and thank you for watching.